So here's a bad looking picture of our yo-yo. There's the outside radius, which I call capital R, and here's the inside radius around the axle, which I call little r. The total yo-yo has a mass of m, and this bright magenta thing is meant to be the string wrapping around the yo-yo. So if we start our analysis by drawing the free body diagram, that's pretty easy. All we have is the tension in that purple string pointing up and the weight of the yo-yo pulling down. So that tells me that the tension minus mg has to be equal to minus ma because it's accelerating downward. But that doesn't tell me enough to calculate the acceleration because I don't know the tension. So I need to go to a torque diagram. So I'm going to draw that picture again so that I can do a torque diagram. So there's the outside radius and here's the inside radius. And I have these two forces here and they're in this diagram. The mg is going to be from the center of mass of the yo-yo, which is also the center of rotation, right there. And the tension, we can see it's being applied to the outside of the axle. So it's right here, the tension. Next, for my torques, I have to do the lever arms. So this is the center of rotation, and I can see that mg has no lever arms. That means it has no torque. So I look for the lever arm for the tension force, and that goes from the center of rotation to the point of application of the force right there. And its length is little r, the radius of the axle. So I can write my torque equation, which is always going to be of the form torque equals I alpha. The same way this is of the form F equals ma, right? So my torque is going to be RT times the sine of the angle, but the angle there is 90 degrees, so I don't have to worry about that. So RT is equal to I alpha. So now I have to think about what I is. It says in the problem that the yo-yo consists of two uniform discs. So if each disc has half the mass, then each disc has a mass of 1/2 m, and it has a radius of big R, right? So each of these discs has a moment of inertia of 1/2 of the mass, 1/2 m, times the radius squared, right? But there's two of them. So both of the discs together are going to have a moment of inertia of 2 times 1/4 mr squared, or a total of 1/2 mr squared, which is not that surprising. So I can plug that in here. I can also plug in the fact that alpha is equal to a over r. So that gives me RT is equal to 1/2 m big R squared a over r. And if I multiply both sides by little r, I have r squared t equals 1/2 m big R squared a. Now, what I want to substitute for in this equation is the tension. So I want to get tension by itself. So I'm going to divide both sides by little r squared. So my tension is 1/2 m big R squared over little r squared a. And now I can stick this in there and get an equation that looks like this. 1/2 m big R squared over little r squared a minus mg equals minus ma. And if I put this guy over here and this guy over there, I'm going to have 1/2 m r squared over r squared a plus ma is equal to mg. And I notice that the m's are going to cancel out because they're in every term. And these now are like terms, so I'm going to have something like a parentheses 1/2 big R squared over little r squared plus 1 equals g. So A is going to be equal to g over this thing, 1/2 big R squared over little r squared plus 1. And that's something I can plug my numbers into and get the acceleration. So that's part A. To do part B, all we have to do is use this answer and put it back in this equation to find the tension. Because since we know the mass and we have gravity and we've just calculated the acceleration, calculating the tension should be easy.